In this video, we'll start looking at what the Spark architecture is and what the backend environment uh, Spark runs on looks like. So we saw this diagram as part of lecture 1, I believe. So let's take a deeper look at it. A Spark application is what is responsible for packaging the logic that you want to run on top of your data together. So that's what is the user program. The application itself is run within the context of a Spark cluster. The Spark cluster itself has, like we spoke about earlier, a bunch of machines which are called as the worker machines, and then they are coordinated with by the master machines. Okay, so the worker machines themselves are running multiple different executors, and each of those executors are effectively one logical unit of physical execution on the worker machines. So in practice, a Spark cluster defines a fixed number of executors to run per worker. So for a cluster of workers, the total number of executors are fixed. Right? Within the executor, there is provision to actually run like multiple different tasks, and I'll come to that in a minute. So the user program that is there in the Spark application, it refers to firstly what is called as the Spark context. The Spark context itself is a reference to the Spark cluster, and when this context is executed for the first time by the running of the execution of the Spark application, at that time the context will have reference to the cluster resources which are necessary for it to run. So that Spark context is what is responsible for creating the references to the data that you need and the intermediate data stores that you will create as a part of processing, the RDDs, the data frames and all of that. So when the context is destroyed, along with it is destroyed all the data that is cached, the intermediate data stores that it's created. So the context determines the life of the data, or the life of how long the data is available. So the Spark application usually is intrinsically tied to the context. So when the Spark application runs for the first time, context is created, and continuous running of the application results in continuous access to the context. So the application gets killed or terminated, context dies along with it. So in some cases, the context can be long-living, in which case the application can come in and go from the front end. Right? So that's a more advanced architecture. We'll come to that at a later point in time. But typically, an application is tied to the context and vice versa. That's how we think about it. Now, what is the nature of the data that the Spark context manages? So we'll discuss in greater depth in the next video. But in effect, it manages references to data of a certain structure, which is called as RDD, or resilient distributed data set. The data frame that we spoke about in the previous video is an abstraction on top of an RDD, whereby you're layering schema, right? You're layering how to interpret that RDD in terms of metadata. That's what makes it a data frame as opposed to just an RDD. The job that you specify on top of that RDD or data frame is a collection of transformations which finally result in a specific action. And we'll look at the differences between transformation and action in the next video. So those get organized in what's called as a DAG, or directed acyclic graph. So the graph refers to the fact that I've got vertices and edges. The vertex here is an RDD. The edge is the specific operation that takes it from one RDD to another RDD. Right? So we spoke about an example of a data frame operation in the previous video, the where clause, the select clause, etc. So all of those are edges in the DAG. The projections is projected data set is actually an RDD. The data set that's filtered is another RDD, etc. Another data frame, sorry. So, but that's how the graph is structured. It's acyclic because you're never going to go back to an RDD from an RDD that's already been created from it, right? So it's always forward moving, and that's very critical to the way the Spark architecture is designed. Because as and when a failure happens, if the failure happens at a particular edge, meaning in the process of doing a particular job, if the previous RDD is cached or ready, it's available to me, then I know for a fact that I can just use that and run the same edge again, right? Run the same processing again. I'll get the next RDD deterministically, like always, all the time. In running the same edge on the same RDD, I'll get the same answer. Right? So that is a very crucial property that's driving the Spark architecture. If you didn't have acyclic graphs, if you had cyclic graphs, which means the same RDDs get changed or the RDDs are mutable, then you wouldn't have this guarantee, right? So that's why it's called acyclic. It's directed because it goes from one RDD to another RDD and it keeps going forward, right? So that's critical as well. So the DAG that gets created gets scheduled on the physical cluster by something called as a DAG scheduler. The DAG scheduler in turn is responsible for breaking the work that needs to be done into stages, where the stages can operate in parallel, and whereas going from one stage to another stage requires data to be exchanged, right? So even though you might actually layer out your data processing as a sequence of steps like this, right? Like where clause followed by select and so on, or a map followed by filter followed by key by, etc. In reality, the DAG scheduler is the one that's responsible for figuring out how much of this can be done in parallel, like multiple different operation types together, or how much of it is gated on the output of a previous stage. So the separation into stages is like a critical activity that the DAG scheduler does, and that determines the optimization potential of your application. So once the DAG scheduler is done with its planning, then it interacts with the cluster manager and figures out which resources were available and then executes those stages respectively. Now let's look at the physical side of it now, right? The workers themselves are broken down into executors like we spoke about. The Spark application runs one executor per application. So think of it as rather one instance of an executor per executor that's configured, and this is going to be scaled up to number of executors per workers, which is there in the config file, and scaled up to all the workers accordingly. That's how the parallelism is built up. So a typical config could say I have a maximum of 8 executors per worker, and my number of workers in my cluster are 10. So which means my base level of parallelism is 80. Right? So my application will run across 80 such instances. Within an executor, I have mechanisms of executing a task. Right? The instance of an executor is unique to an application. A new Spark application comes in, it registers, or rather it gets executed with the master. The master then allocates what's called as a driver program. The driver program runs on the master node, which then creates the DAG for the operations that are embedded within the user program, and then the driver coordinates with the cluster manager to get the instances of these executors, and then the stages which are broken down are executed as tasks within those executed instances. And then once the entire set of tasks are done, all the stages are done, then the final execution returns back to the driver. Intermediate executions also could be coming back to the driver for certain needs. Like for instance, if you have the need to show outputs of intermediate data frames, then the show operation actually happens as an action and gets accumulated back in the driver program. Whereas for the most part, all the transformation actions actually happen on the worker roles, right? So that way the parallelism that is maximally available to you, which is in the worker cluster, is used for data processing, right? And then once the application is done, the entire set of executed instances are freed up, and then the cluster manager is informed about it, and then the application closes out, the context is cleaned up. The executor instances also have a cache. The cache is shared across multiple tasks. That's how you have optimization opportunities available to you, whereby data that's created as part of a different functional logic within your program can be used in a different part of the logic by referring to a cache if you have cached it, right? If you have persisted that data in the cache. So this cache becomes very useful for the tasks to exchange information within the executors. The cache also becomes the destination in case you exchange data between cached data objects across executor instances across workers. So the distribution of data becomes faster, even though it traverses the network. It doesn't have to write to disk, it just actually gets stored in the cache. Yep, so that's in terms of the Spark architecture. Let's take a look at the machine types in a bit more detail and the processes that happen. I'm going to go to the Spark cluster overview URL for this specific information. So you can browse these on your own, definitely. So before we get further, let's just go through the glossary in a bit more detail so that we are very precise. Right? The application that you launch on the Spark cluster is the user program, right? That's built on Spark. Behind the scenes, internally, it's broken down into a driver program and the executors on the cluster. So the driver program runs on the master node, and then the executors run on the executor nodes, on the worker nodes, right? The application itself is packaged as a jar. The jar is just the conventional term that's used, but if you use Python, the Python also actually gets converted to like a jar file along with I believe it uses one of the Python Java linkages called as Jython, but I'm not sure about that. Yeah, but anyway, the jar is created keeping in mind all the application programs. Sometimes it also creates what's called as a Uber jar. Uber jar is like a collection of all jars which have dependencies like libraries and all of that, and then it ships it all together. Right? The driver program is typically denoted with a part of the program that starts with the main function. And it's basically the program that the part of the program that sets up the Spark context. If you're not familiar with like the notion of driver and executors, the way to think about it is wherever you touch data, and the data can be large in scale, that's the part that you want to run on the executors. But for everything else, like the control associated with it, the summarization, the certain operations which look at only portions of the data for sampling, for being able to look at the data visually, those are the parts that typically run on the driver, apart from the starting of the program, which is setting up the context, the configuration associated with the application, etc. The cluster manager, like we spoke about before in the previous video, could be in the typical case as Yarn, but in many cases, especially on public cloud, because it's containerized, it could also be Kubernetes, right? So it's perfectly fine. Worker mode, we spoke about that, any physical machine that can run application code. The executor is the process that's actually launched in the worker node, right, on behalf of a particular application. This is the one that runs tasks and keeps the data in memory. Each application has its own executors. So if you have multiple applications running at the same time, each will have its own executors being spun up. Remember that I said configuration is static. So the number of executors in a specific cluster is fixed. So when the Spark application runs, all those executors are getting assigned. If you have another Spark application that's running at the same time, those executors, new executors are getting assigned as well. So you need to be careful about how much parallelism is happening. While the DAG scheduler and the cluster manager work it out for you, beyond a certain range, you start running into out-of-memory problems if you have too many executors running in the cluster. So the task is the unit of work that's sent to one executor, but really the job is what you want to look at. The job constitutes the set of operations that you perform leading up to an action. So in Spark, the transformations and actions are treated as two different sets of activities. We'll take a look at what those examples are in the next video. But in effect, the job is delimited, or a job is determined by a sequence of transformations that lead up to an action. A user program can comprise of multiple such jobs. But a job is executable on its own, but not anymore, because the action determines what needs to happen next. So that job, which comprises of those transformations leading up to an action, gets organized in the form of a DAG, right? And then the tags are broken down into stages which get executed on as tasks on the executor nodes in the worker. That's how you think about it. Now, if you really take a look at what the tag looks like, so here's an example, right? So what I'm doing here in the Spark program is I'm taking the Spark context, which is SC, and in that Spark context, I'm taking the numbers 1 to 100, the array 1 to 100, and I'm creating a data frame by invoking the parallel version of the array, which is called as parallelize, with the functions parallelize, and I'm converting that to a data frame. And then on that data frame, I'm doing a count. So obviously I'm expecting the answer is 100, right? So it's a toy program, but the toy program is intended to demonstrate to you what does the tag look like, right? So here, the tag is being created without any, what do you say? There's no input data frame to it. You're actually creating a data frame from scratch by picking up constants. The constants here are 1 to 100. Yeah, so on top of that input, you've created the data frame for the first time. That's this 2df function. And on top of the data frame, you're executing a data frame compatible aggregate, which is a count function. So if you look at it as a job that needs to be run, the count is the aggregate. So the count terminates the job effectively. The transformations that are required are just parallelized in 2df. The count is requiring the final count to be computed, which means there is data that needs to be exchanged. Because the data frame is actually a distributed object across the Spark cluster. So the count is not complete until I've received the partial counts from each of the machine. So if you look at it as a map reduce operation, the map is basically doing partial count. Actually, the map is just a scalar map. The reduce is doing a partial count on each of the different workers. And then once you get the partial count, I shuffle the data, bring all the data to one machine as an example, and then do a count again. So I do another reduce operation to get the final answer. So that's how the stages are broken out. Okay? So this job is broken into 2 stages. Ignore the stage numbering. That is an artifact of how internal stages are represented within Spark. But the key fact is that there are 2 stages for your job functionally. The first stage is responsible for running all the steps leading up to the data frame, because that can be done in parallel. Right? And once that's done, then you go through a sequence of exchanges of data, because you need to exchange the partial counts, and then the final count is computed as a final set of data, final operation that happens. Right? So that's why this kind of a job has 2 stages. So the DAG is responsible for figuring out which parts of it run together, which parts of it is gated on data to be exchanged, which part of it can be parallelized. So that's very sophisticated logic actually. So now imagine if you now run machine learning operations, right? So Spark has built those operations or those algorithms to leverage the native functions available within the Spark libraries, so that you benefit from being able to get large scale optimizations with the stack scheduling that you see here. Alright, I believe with that we've covered the DAG scheduling. We've taken a look at how DAGs are configured, rather determined. So the role of a cache is interesting. So remember we spoke about Spark in lecture 1 as evolving as an alternative implementation of divide and conquer compared to MapReduce, the Hadoop MapReduce, because the Hadoop MapReduce system was writing to the file system for every single intermediate data, and as a result it was resulting in a lot of latency for large scale data processing. And Spark optimized for memory access, and in return it gave a significant boost in performance, because you don't need to write to disk for every single operation type. Now that is an artifact of leveraging the memory that's there in the worker node, and specifically the cache that's available to all the tasks that need to execute one by one as part of the jobs that execute in that application. So the first job that it executes, let's assume that it's doing something really complex. with the data. So let's take the Indian Railways, the IRCTC ticket booking data. So the data is available as files on HDFS or on the public cloud storage systems. And because the data is very voluminous, I don't want to keep reading it again and again and again, right? So let's say I'm running a program that does two things. One, count ticket booking by state. And second thing it does is, it also sums up my total revenue, right, that I earned that day by summing up all the payments that I made. If you notice, for both of those tasks, the input data is the same. Input data is basically the IRCTC ticket booking data. The input data is available as a huge cluster of, rather a huge set of files spread across the entire Spark cluster, right? Spread across the HDFS or cloud, public cloud, whatever it is. So when I read the data, I'm going to incur the cost of reading that mass of data, like let's say it's terabytes of data, right? But when I compute the answer that I need finally, which is ticket bookings by state or total sum of revenue, it's actually a very small data footprint as output compared to the volume that's coming in. There are two ways in which I could write this. The first way in which I write this is two separate Spark programs. One Spark program only does the count by state, the other Spark program only does the revenue sum. In that kind of a scenario, both these Spark applications will run their own executors. They will each read from the source, which is basically the HDFS, the entire mass of data, only to do an aggregate computation, which is resulting in a small volume of data that gets output. So the total runtime for both these applications will be limited by the speed at which you can read the data from the file system. And that is going to be applicable for each of these applications. Now, imagine another way of writing the same program. In this program, there's only one Spark application. That Spark application, in its first job, reads the data from that S3, HDFS or S3 or GCS, whatever cloud storage is, and reads it and creates a data frame. It's not still performed any action on top of it, it's just read the data, right? So it's like read.csv as an example. So once it's read and got into a data frame, then there will be two different set of jobs. One job only to do the sum of revenue, another job only to do the count per state. Because both of these require the same input data, it can refer to the same data frame that I've already read. Because the data frame that is read is going to be used for both of these jobs, and those jobs have their own parallelism, have their own stages to execute, I can choose to cache that particular data frame that I've read from the disk, right? The ticket booking raw data. So if I choose to cache, then I've effectively created a copy of the data frame in the memory across all the executors in that application. I mean, that is assigned to that application across all the workers. Then the next job that runs and the next job that runs is going to refer to the copy of the data that's in memory, distributed across the workers. Imagine the speed up that it's possible, right? At the minimum, you're going to avoid having to read all of the data from disk again at least once. Right? In the other approach, you would read it twice. Here, you would read it exactly once, and then from that point on, you would read it only from the cache. So tremendous performance benefits, it's possible. Now, this assumes that the data is actually possible to fit in memory. And here's where a common Spark problem occurs, right? Sometimes the data doesn't fit in memory, but you think it does, and in which case, what Spark does, because backend uses Java backends, it spills over to disk. And when it does, sometimes the disk is so slow, or the spilling over results in what's called as thrashing, because multiple applications are trying to do the same thing. All of it is trying to spill over to disk. So all the time the data is getting evicted, etc., etc. So that results in out of memory issues for some of the large scale applications, when especially resources are running tight. So you have to be careful about when you cache, and you can actually have a lot of options available for you even when you choose to cache. Like for instance, you could cache such that the some of the data is in memory, some of it is in disk. You could also cache with intermediate middleware technologies, which solely serve the purpose of giving you accessible storage areas which are very fast, like flash disks and SSD disks, etc., which allow you to serve the role of a cache much more effectively, and in a way that's off Java heat, right? So those are all like advanced topics. You can look it up if you're interested. But yeah, cache management is an effective and efficient feature that's available as part of the Spark application. Alright, so with that I'll stop this video. In the next video we'll start to look at some of the Spark implements.